Alrighty, so welcome to the second half of Unit 4, and that's going to be dealing with random variables. Now, in the first half of Unit 4, we talked about probability and rules that happen in the long run due to the law of large numbers. Well, now in random variables, we're going to be looking at chance processes and how to quantify these chance processes through probability models and probability distributions, which you can see are some of your vocab terms for this unit. We'll also be looking at the difference between a discrete random variable, which are countable values, and a continuous random variable, which is an interval of values. So here's some vocab for you, and we're going to get right on into it. Thankfully, random variables tend to follow the same probability rules, so this is going to serve as a good review for us. Now, suppose we are flipping a fair coin 3 times, and we're going to let x be the number of heads obtained. So when you flip a coin, you have the following outcomes. If I flip it 3 times, I could get 3 heads in a row. Or perhaps I get 2 heads in a row and then a tails. Or perhaps that tails comes in the middle. Sorry, y'all, I'm kind of cheating with my notes here. Or maybe there's 2 tails. Or maybe only 1 tails, 2 heads, or the heads happens in the middle. And the way I found these outcomes is I just actually used a probability tree to show me the different possibilities. But let's see here in our sample space. We have 1, 2, 3, 4, 5, 6, 7, 8 outcomes. So these are all the possibilities here. And my sample space is supposed to go right here, y'all. I'm sorry. I was just so excited about random variables. Okay, so we can have no heads, 1 head, 2 head, or 3 heads. Now, of these 8 outcomes, probability of getting no heads is going to be 1 out of these 8. Probability of getting all 3 that are heads is 1 out of 8. And let's count the number that has 1, and that's going to be 3. And then same goes for 2. So I can see here's my valid probability model. And again, I'm checking are all the probabilities between 0 and 1. Check, and do these add up to 1. So 1 plus 3 plus 3 plus 1, that's 8. 8 out of 8 is 1. So we've met the conditions for a valid probability model. Alrighty, so now let's take a look at some of the probability rules. It says find the probability of obtaining 2 or more heads and flipping a coin 3 times. Now, 2 or more, that's going to be inclusive, meaning that that 2 is going to be included in the value. So when I write my inequality, probability of obtaining 2 or more looks something like this. And I'm going to see in my random variable distribution that the only way that can happen is if I get 2 heads or if I get 3 heads. Now, notice I said the word or, thinking back to our general addition rule. But looking at these events, since it's a probability model, a very basic one, these events are all mutually exclusive, meaning that you either get 1 head or you get 2 heads. You don't get 1 and 2 heads. It's not possible. These are mutually exclusive events, which means for our general probability rule, the addition rule, we're just going to be able to add the probabilities together. So now that's going to look like 3/8 plus 1/8. So that's going to give us about 4/8 or 1/2. So these are mutually exclusive events when looking at a random variable distribution. Now let's take a look at the next one. Find the probability of obtaining at least 1 head. So here, at least 1, thinking back to our probability rules, is the probability of obtaining at least 1 means 1 minus none. So the probability that we obtain at least 1 head is going to be 1 minus the probability that we obtain no heads. And the probability that we obtain no heads, that's if we get tails all 3 times, that's just going to be 7/8. So those are just some ways that we can use a probability model, and you can see there's the at least rule, the complement rule, mutually exclusive events, and we could even do conditional probability if we wanted to, but that's a little too spicy for this intro lesson. So just some examples there. Now, notice this is a random chance process, and looking at the distribution, it looks approximately symmetric, since I can see that the probabilities are mirrored of one another. So when we described a distribution back in Unit 1, we looked at things like the center, the shape, and the spread. So I can tell my shape here is approximately symmetric if I were to graph this in a histogram or even a dot plot. But what I need to figure out is how I can interpret the center and the spread. Well, I just said it was symmetric, and we know that if a distribution is symmetric, we should use the mean and the standard deviation. So what's going to happen now is that I'm going to go here. And on our AP Stats formula sheet, we're going to be focusing on this area. So section 2 is probability and distributions, and lo and behold, we have our conditional rule and our general addition rule. And we also have different types of distributions here. We're going to be looking at the mean and the standard deviation for a discrete random variable. Good news, you will have this on the AP exam and in class, so you don't have to bother to memorize any of these formulas. So all good there. So suppose here, when we're describing the center, we're going to use the mean, and not all of the random variable distributions are symmetric, but we do have this formula that gives us the long run behavior of the random variable distribution. So let's suppose I have different x values and their probabilities. This formula here just tells me that I'm going to take the sum of each outcome multiplied by its probability, and that will give me the long run average. So in the long run average, we expect the blankety blank. Now, things to note are that looking at this notation, it can be the true average, the mean, or it can be the expectation, but this is going to refer to our center, is the mean or the expectation. Now, to describe our spread, we will use the standard deviation, but to get there, we need to find the variance first. So the formula looks a little scarier than it actually is. This just says you take the mean away from the observation, because we know that the standard deviation is how much each observation varies from the mean, typically on average. So here you can find the variance first and then take the square root to find the standard deviation, or you can just go straight to the computation. But here we'll say something along the lines of, in the long run average, observations typically differ from the mean by about this many units. So to describe the shape or any unusual features, we are going to actually graph the distribution on a histogram and then proceed from there to describe those. But as far as the center and the spread, we have mathematical formulas to help us determine those quantities. So let's take a look at an example here. Let x be a discrete random variable that follows this distribution. When x is 5, the probability is 4k, 10, 3k, etc. So it says find the value of k that makes this a valid probability model. Well, look at each of these. These are my sample space outcomes, meaning that the sum of these outcomes must be, you guessed it, they should be 1. So I'm going to take 4k plus 3k plus 2k plus 1k, and that should give me a total sample space probability of 1. 4 plus 3 is 7, 7 plus 3 is 10, so I have 10k equals to 1, which means if I solve this, k equals 1/10 or 0.1. So that will now give me the correct probabilities when I sub in. So I'm going to take here, and so accounting for my original x values, that was 5, 10, 15, and 20. So 4 times 0.1 is going to give me 0.4. 4 times 0.3 is 0.3. 4 times 0.2, and then 1 times 0.1. Notice 40, 30, 20, 10, that will add up to 100%. So we have a valid probability model. Now, to find the mean, we are going to do 4 key parts. The first part is we're going to talk what we're looking for. I'm looking for the mean or the expectation. Next, I'm going to show the formula that I'm using, and I'm just going to copy it here from my AP Stats formula sheet. So I'm just going to say x times px. Now I'm going to show some substitution. So that's going to look like 5 times 0.4 plus 10 times 0.3 plus 15 times 0.2 plus 20 times 0.1. And if I were to type these values into a calculator, I would get that the mean of this distribution, pausing for technical difficulty so I can find the answer here. Alrighty, and we are back with that. So after I compute these values in a calculator, I get that my mean is going to be about 10. So I would say in the long run average, x should be expected to be about 10. Alrighty, so now let's take a look at the standard deviation. Again, I'm going to just copy from my formula sheet. So the standard deviation is going to be the square root of the sum of each observation minus the mean. We're going to square it to exaggerate the differences, and then we're going to multiply by its respective probabilities. Now I'm going to be honest with you, it is tedious to find the standard deviation by hand, and typically for random variables, they're just going to ask about the expectation, but you never know, it could happen. So the good news is we only need to show the substitution for the first one and the last one. So the first observation was 5, so 5 minus 10 squared times that probability was 0.4. And I can skip the middle two, and then, so this ellipse here just means there's more values. And then here at the last one, that's going to look like 20 minus 10 squared times the probability of 0.1. And I don't know why my pen is curving, but if I were to also put this into a calculator, I would get 5 for my standard deviation. So in the long run average, observations tend to differ from the mean by about 5 units for this distribution of x. So that's just an example there of different variations. So the first thing was finding the missing probabilities. To find the mean, I multiply them, and then to find the standard deviation, I use this handy dandy formula. But now look, I have a valid probability model, and again, mutually exclusive events. So I can actually now apply more rules of probability here. And so here it says, find the probability that x is greater than 5. So that x is greater than 5. I don't know why that looks so wonky. Well, looking at my distribution here, the probability that x is greater than 5 would be 10, 15, or 20. And so if I want each of these values, that means I could ignore the 5. And so I can actually just use the complement rule. So I will take 1 minus the probability that x equals 5. And that's going to give me 1 minus 0.4. And that's going to give me about 0.6. Now, the alternative method to this is that you can just take x equals 10, x equals 15, and x equals 20. And you can just add those probabilities together. So notice that 0.3 plus 0.2 plus 0.1, you guessed it, it's still going to give us 0.6. So it's completely up to you how you want to approach these distributions. You can use the complement rule, you can use the at least rule, you can use conditional, general addition, mutually exclusive, etc. But you've got a repertoire of tools now in your probability knowledge per se. So this is what we call a discrete random variable. Notice that each x value takes on a exact value. So these are examples of discrete random variables. And in the next part of the lesson, we're going to talk about continuous random variables. So stay tuned.